Cool. So, for those of you who were here last week, I gave a much longer sort of introduction to the software because I think something like AutoCAD, you probably don't really know where it sits in an industry context or how a practicing engineer might actually use that software. Something like a structural analysis program, a space gas that we're going to look at today, it's going to be much more obvious. This is the computational version of the structural analysis that you've all been learning since the first year of your structural engineering program. So it's really the bread and butter of any design engineer, particularly a design structural engineer, but geotechnical or civil as well. And you know, any of you, if you're out working design offices, or even if you're working in more like site or construction facing roles, it's a really fundamental tool that you're going to use almost every day. Space gas, actually maybe just a quick show of hands in the chat, if I can figure out how to pull it up. Who has used space gas before, either in their third or fourth year of program, and who isn't familiar with it or is perhaps in the earlier stages of the structures program? Bit of a mix. It's not the only analysis software out there. It's one though that's very popular in Australia and is used pretty much exclusively at most small to medium structural engineering firms, and is used at most of large-scale structural engineering companies, although they'll typically also have other in-house softwares that they'll access as well. So for Arup, it's Oasis GSA. For GHD, it's more robot structural analysis, which is the Autodesk version. And there's others in Europe, MicroStation, MicroStrand, and SAP 2000. They're all more or less the same, right? So what we're talking about today, even though it's specific to space gas in terms of how you pilot it, I'm going to try to lay it out in terms of things that are common to every structural analysis, regardless of whichever program you do it. The one thing I'll say though, before I really launch into it, it's a 3D solver. So all of the typical softwares that you use in practice are three-dimensional. Softwares like ISA, or Instant Structural Analysis, which some of you might have seen in your second year courses, that's a really simplified software, and it's so simple by constraining the whole thing to 2D. It actually doesn't require you to learn a lot of the kind of nuances of using a full 3D solver, and most of the areas that you'll get, or problems that you run into while trying to learn space gas, occur because it's a 3D solver. So if you can, jump into a 3D solver while you're still at uni. You have ample opportunity to use it in your third and fourth year courses, and it's free for you to download if you're a student. Unfortunately though, most of them only run on a Windows machine. So if you have a Mac, I'd recommend installing Parallels, so you can install the software on your home computer, or try to get access to a Windows machine. Unfortunately, obviously, you can't get into campus to use the EAC computers labs at the moment, but otherwise, in the future, hopefully in the near future, when you are getting back to campus, this software is installed on all of the EAC PCs for you to use directly. So, firing up Space Gas, this is version 12.85, which is the latest one. It's free to download for all students, and your download is the full version, so it'll run without constraint. You'll open up a screen like this, which will show your origin axes. It's got similar view tools to what we talked about in AutoCAD last week, so you can pan and view in 3D. But the first place that you always start with any analysis software, and you saw this as well as the first place to start with AutoCAD, it's the units. So the choice of input into your model is very important. A lot of your education, or at least your manual learning, you might have been working in, say, newtons, millimeters, megapascals as a consistent set of unit, or SI units where you're looking at newtons and meters and pascals. Both of those are consistent sets of units, which means that when you work through the calculation manually, you don't need to factor up or down by factors of 1,000, for example. Space gas doesn't by default use a consistent set of units. It uses what I would call a natural set of units for a structural engineer. So your overall lengths for your structures are in meters, but your section properties are in millimeters, right? And that's a pretty natural way to define both of those systems. Your material strengths are in MPa, Your mass density is tons per meters cubed. Again, that's a pretty natural way to define those units. The thing that might trip you up, or is what gets students in my course in third year when they start comparing their computational results to their hand calculations, is the kilonewtons and kilonewton meters. So kilonewtons is not used in any of your analytical solutions. It doesn't sit in the SI unit or the Newton millimeters consistent units, but it's a very natural standard kind of dimension for a structural engineer. You know, it's of a reasonable magnitude for most of our applied loadings. And obviously if you're working with wind pressures, kilopascals, it translates fairly naturally to kilonewtons as well. So just be mindful of the system of units when you start. If you have a preferred one, you can obviously change it. But the good thing about space gas is that when you start actually inputting some of this information, which I'll talk about in a moment, it's pretty good at actually telling you what units it's assumed that you're working in. So modes, for instance, are in meters. It reminds you. You know, a lot of softwares, particularly finite element softwares, AutoCAD even, they don't include these reminders for what units it wants. You kind of have to remember the setup, but space gas is really designed to make it convenient for you to actually remember what numbers you're meant to be typing in. So the units is where you start, but after that, for structural analysis, you'll need to be defining a geometry. So this first menu here in structure contains all of your geometry creation tools. There's certain classes that you're not going to need in your undergraduate degree. So particularly the mesh and plate tools, your master slave constraints, or your plate tools. That kind of thing is sort of more a slightly advanced level of analysis. It more relates to the finite element method that you might see as an elective in fourth year, but the main geometry that you need to be thinking about is your nodes and your members, right? So your stick frame geometry that will model your, most of your steel structures and a reasonable number of your concrete structures as well. I'm going to use the structure wizard briefly, and then I'm going to come back and show you the manual creation method. But space gas has a pretty decent parametric library of structures. So for a lot of your standard kind of systems, which might be trusses, portal frames, multi-story frames, it will generate the system for you. So if I start with something like just a simple truss, it actually allows you a decent parametric input, which specifies all of this information for you and flashes up a nice model, which is actually more or less good to run straight away, or at least as soon as you've assigned loads. The thing that I want to point out here is that by default, it actually isn't showing you the useful parts of this model that you really need to be looking at. So apart from units, I'd recommend changing your display mode back to a wireframe, at least initially, turning on your node restraints, which are your boundary conditions, obviously pretty important, turning off your origin because that's not really important, and then finally showing the member fixities. So the member fixities and the boundary conditions are really, really key parts of performing your structural analysis correctly, particularly member fixities, because when you're learning to use the software or you're a junior structural engineer, it's one of the most difficult parts to analyze or get right. And if you don't include them or you can't see them, it will still run the analysis and you'll still get a result. If you miss something like a boundary condition, if you miss a member property, if you don't apply your loads, it won't run, or you get a result that's obviously wrong. If you miss a member fixity, you get a result, but it will be more difficult for you as a junior engineer to kind of spot the mistake. So always, always, always make sure that you're working with member fixities and boundary conditions displayed at a minimum. And I don't know why it's not displayed by default. But I just wanted to use the wizard because it allows me to introduce that up front, but I'm going to delete everything. Oh, no, look, I won't delete it. I'll show you how you can input this information yourself manually. So you can draw your geometry. You can draw your members by connecting between two elements or two nodes. If you hover over an element briefly or over a connection point briefly, it will perform a snap but it's not as intuitive as AutoGas. You have to wait for a second, and then you'll hear a little popping noise, which indicates that it's connecting to that node, and it'll flash up the dimension. So don't just click near it because it won't actually connect. Make sure that you hover. So members are pretty straightforward to input yourself, but if you're drawing nodes, it's an absolute nightmare to try and get these positioned in the right location. So I'd never use it. You might use it if you're particularly confident with your mouse drawing, but I'd always use a data sheet as a way of actually drawing my nodes. And you can see the nodes are stored in a pretty normal format, node 1 to 10, X, Y, and Z geometry. The wizards generated pretty sensible nodes. They're located at 2 meter widths or 2.5 meter heights or vice versa. But the nodes I've clicked, they're not assigned to any sort of grid system. They're just nonsense. So in terms of developing a precise model, I definitely recommend the data sheet. In terms of actually inputting your information, if you can use something like an AutoCAD software, that has a fully fledged geometry drawing capability. So you can draw your geometry for, say, a complex structure in a CAD tool. You can export your node data, and then you can input it to the space gas. So these softwares aren't designed for drawing really complex geometries, which is why they have fairly simple geometry input tools, but they have very robust geometry import tools. So you can copy, paste, and import all of your node data just from a spreadsheet or from a CSV export from a CAD software. But for the standard that you're probably looking to use it for your coursework, certainly most of the geometries you're asked, you should be able to draw manually. Members, in terms of the data sheet, it has a lot more information in terms of what you need to input when you create an element. But the key columns for you to pay attention to are node A and node B. So where is the column starting and ending? That relates to geometry. These remaining parts, section, material, and fixtures, I'm going to talk about them separately in member properties in a second. So units, geometry, basic graphical interface are fairly simple to get up and running with. Use the wizard initially, but with caution, in particular paying attention to this other information that it's creating for you. We're about to cover that though as a manual input in a moment. But just to check in, are there any questions so far?
No, none from me.
All right, so continuing straight through, the next aspect, so units, geometry, properties. Space Gas has this property tool over here, which isn't much good to you until you actually click on something. So clicking on a member will give you member properties. Clicking on a node will give you node properties. They're both important. Nodes are where you define your boundary conditions. So you can see in this roller support over here, it's created for me a fixed roller support. These letters correspond to your X, Y, and Z translations. So X translation, Y translation, and then out of plane translation, Z. And then the last three letters correspond to your X, Y, and Z rotations, or rotations about those axes. R is released, F is fixed. So if it's released, it means that it's free to move in the X-axis, i.e. it behaves as this roller here. If it's fixed, it's not allowed to move in that axis. So it's prevented from movement in Y, and it's prevented from movement out of plane in Z. So it's a 2D roller, but it's adding an additional constraint out of plane, which allows it to be analyzed in a 3D system. Pin supports are fully pinned, so all translations are fixed, but rotations are constrained. When you're analyzing a 3D system, you'll typically need to add extra supports. In this case, essentially what I would call an out-of-plane roller support, which is this last one here, which prevents the structure from moving in the Z-plane. So you're blocking the structure against movement. This way, that stops a rigid body rotation about X, and it also stops it having any movement in the Z-plane, which you don't want for a 2D problem. This one over here does the same, but it's added an additional torsion constraint, which again just helps the structure, remove some instabilities, but probably you don't need that for this question. So nodes, you apply your standard constraints like you'd expect, but you're operating a 3D system. So you've really got to be mindful of what these letters actually mean. But these first three standard buttons, fixed, pinned, and roller, they will automatically choose the correct restraint for your problem, assuming you're working in 2D, but they'll apply in 3D. So these three really should cover most of your cases, with sometimes needing this additional out-of-plane support to help you operate in 3D. So node properties are your boundary conditions. Member properties are much more robust. And I'm going to start with the basics here, the section and the material, and then I'm going to talk separately about your member fixities. From really your second year structural mechanics courses, you've done a lot of work in section analysis, so calculating major and minor principal axes, which then relate to your flexural properties, your flexural strength and your flexural stiffness. Part of the reason that space gas is really popular in industry is because it's an Australian design software, which means it has a really good Australian catalogue of section sizes. Like the default sections are the default Australian steel sections that you can access as a typical Australian engineering company. It's got a few other catalogues. It's got India, Japan, New Zealand, British, China, Euro sections. They're all broadly similar in that there'll be I sections, there'll be universal columns, universal beams, circular hollows. The difference will just be the local manufacturing ecosystem. They'll produce slightly different versions of standard depths or standard widths or standard thicknesses. And as an engineer, you don't actually get to exactly choose every parameter for those typical kind of consumer grade elements. You're constrained to the manufacturing ecosystem, which are these standard dimensions here. There are plenty of situations though, even though standard sections might cover 80% of your design work, you always encounter situations where you need a custom section. Pretty much every job you might need to do. This second tool next to the book, so they're very subtle tools. The book's here, that imports from the library. This tool right next to it, it's a little I-beam with a C on it. That's the section builder. So that allows you to create your own custom section, which comes up much more often than you think. The standard shapes correspond to your standard thin-walled steel shapes or your standard concrete shapes. So you have like box girder, which you might use for, say, a concrete design, hollow sections, which you could use for a concrete or steel design, say a concrete column with a surface penetration running through it. And then you've got your sort of cold form steel sections for roof purlins or lightweight structural elements, which your Z shapes, your C shapes, and your hat shapes. So you can build pretty much any section you want parametrically, and you can also build it up as a compound section. So 10. So if you have a section that's composed, say, of two steel elements, here about Z, there, you can build your compound section by inputting it exactly. And in fact, if any of you are in your early years of your course, Civil 2330 particularly, you can use this information to check all the questions that you're getting on calculating section properties and so on and so forth. So it's a super useful tool. Of course, you can calculate this all analytically, but I trust this software before I would trust any of you with a parametric spreadsheet. Saying that as someone who's written parametric spreadsheets to calculate all of these I-beams and C-section properties, I'm still finding mistakes in it. Having said that, of course, if you're calculating a custom element for a job with a pretty significant aspect or risk in that design, you always want to be checking these numbers that the computer is throwing up for you, simply because, you know, most analysis software, it's obviously constantly being developed and it's constantly being bug fixed. So the more complex a parametric tool that you're relying on, the more potential there is for there to be mistakes within that, and the more careful you should be in error checking with manual calculation if it's something that might play a significant aspect in the overall structural performance. Thin walled steel sections, though, you know, short of a really critical aspect of a design, I'd be fairly confident in using most of these parametric library tools. So let's ignore all that. Go back to here and look at material properties. So section properties, oh sorry, one final note on section properties, this button here. You spent, you know, a good 2 weeks of your structures education looking at major and minor principal axes, and then that wasn't closely looked at for the rest of the course, but you need to control which way your section is being oriented. And typically it's at 0 or 90 degrees, the major or minor principal axis, and your transposition tool allows you to specify that. It'll swap, if you look closely at I, Y, and IZ, it will swap those two back and forward. And in 3D, it will then swap the correct orientation to kind of allow you a more intuitive check of the system.
What if we were to just change the direction in the member properties tool? Is that the same thing, or?
Yes, so up here, this one.
Yep.
Apply that, same thing.
Yep.
The difference is, you saw there, that's changed it for a single member, member 12.
Yeah, so if you just selected the other members, it'd be doing the same thing?
It'd be doing the same thing. Whereas if you change it in the section tool, section 4, that changes all the sections that it's attached. So that's a really good question. And that also shows you that, I guess the related comment there is your major and minor principal axis aren't determined based purely on this. You can also rotate your individual element to a specific orientation. And so obviously if you rotate this by 90 and transpose the section, you've done actually nothing. So the 3D tool is kind of helpful there. But also, you know, you really need to make sure that your own understanding of what's the section axis that it's rotating about, what is my section property input here doing, you know, that's kind of a related thing. So you can use the 3D tool to kind of check your own understanding of the data being input there. You've just reminded me of a second really key point, is this number here. So I haven't actually mentioned that. The section, even though it's input as a member attribute, it's its own property data sheet that's specified here. Oh, sorry, that's material, structure, section properties here. So you can independently input your section attributes, and then this number, this number actually then points it to the corresponding attribute that you've designed. So if you've already input a section property for, say, this top flange, that element is now pointing to that first section property here. And these color codings correspond to your section definition. If that means that if you want to change a particular element, just watch the section grouping, because if you want to change this one and you change it in the section attributes, you'll accidentally change it for all other elements which use that number. It also, though, is beneficial because it means that, you know, you're typically designing these 4 elements. It's not, you're not going to be designing them individually. You'll be looking for the worst case element. So it might be this one or it might be this one. You can use the section attributes to kind of automatically process your results and then pull out maximum minor loads for that section type rather than by individual members. It's a little bit tricky, but if you're into that kind of thing, I'd recommend watching the Python workshop next week, because that's kind of a very useful tool in helping you to process or build up interoperability in terms of how you might connect, say, Space Gas results or Space Gas member numbers to some outside software ecosystem. Sorry, yeah, was there a question there?
So what other softwares would you want to link that to? Because yeah, I haven't really seen examples of that myself.
No, and I was actually, I was going to mention this at the end, but I think it's really fantastic that CESA is organising a Python workshop, because the most powerful use of these tools is with some scripting subcomponent. Now, Space Gas is annoying to me as someone who's a little bit more at the computational design end of structural engineering, because it doesn't have a great API, which means that for people who want to use the software from a scripting interface, loosely speaking, you can't automate the model analysis. There are other software tools which have a similar functionality, a lot of finite element packages in particular, and you can actually run your entire model from Python, or you could run it from Excel, really, even if you wanted to. And then you can automatically build your model, analyze it, and then get your results back out without necessarily having to open this interface and put it in manually. On the flip side, you could also sit outside the software and you could have a nice, steel design spreadsheet set up, or a steel design Python library, which you can use to parametrically control all of your design calculations. And you can pilot, some softwares from outside using scripts, and then again, automate it that way. That's quite advanced. What I'd recommend is something that's actually common in practice is exporting your results from Space Gas, which I'll talk about. They might be text-based, or you might be able to copy-paste it, put them in a spreadsheet, and then build some simple spreadsheet automation tools, using Visual Basic or some of the inbuilt Excel tools.
Yeah, I think a VBA tutorial would even be pretty helpful as well.
VBA is the #1 most common entry-level scripting use in structural engineering offices. Python
I actually had
is a very close #2.
My boss just said to me, actually, if I'd ever used it, I hadn't. So there you go. I'm going to be going home and learning about that tonight.
There you go. So, and that's where I started, but it also has its limits. VBA, and Python, I would say, is more robust and transferable. So it does all the things that Excel does. It has a steeper initial learning curve, but then you can do a lot more with it. But it's also, the flip side of that is why something like VBA is so popular in structural engineering practices, because you're using the spreadsheets anyway. All your information is tabulated, either in your data sheets in Space Gas or your sort of nice spreadsheets that you're creating in Excel. It's an easy extension to start looking at VBA in terms of how to script some useful tools to help process that data. And Excel also has a macro record function, which helps you get started really well. So that it is so really, I guess the learning curve in terms of increasing your capacity to automate or batch analyze a bunch of models, or connect your analysis to, say, a geometry design module and then a structural design module, VBA to Space Gas or VBA to Excel to Space Gas is a common link. And then Python to literally anything is a very common link as well.
Yep, sweet, thank you.
So no, that's a really good question. And it also answers maybe something else that you're thinking of is, do you have to literally spend the next 5 years of your career inputting this data again and again and again, right? Like, if you're thinking typical structural engineer, if you're working on small and medium scale jobs, you're going to be running, many Space Gas models per week. It's going to get pretty tedious pretty quickly, having to create them all each time. But equally, what I'm talking about here, even though it's taking me half an hour, once you get good at Space Gas, it takes you 5 minutes to run through all of your setup, right? All these member attributes, most of them are pretty standard. A lot more of the engineering work is in your loading and then design afterwards. So that is a precursor. I'm going to jump ahead. So in the interest of time, you can input your material properties. Steel is standard, but this has all the basics. Concrete of different grades, timber, aluminium. pay close attention to it. You can input it manually. Member fixities are the number one thing that junior structural engineers get wrong. There is no right member fixity. It depends on your connection detail. If you're designing a web plate connection, which allows rotation, doesn't transfer moment, you need to use a pinned release, which allows rotation in the relevant axis, normally about the z-axis for 2D systems. If you're using a welded end connection or a flange plate end connection, which prevents moment, you need to make sure that's fully fixed. There's a whole course on this at 3340 because it is quite tricky. But as you're learning to use it, the reason I pointed out is the two most common errors that you're going to get if your models don't run. You'll get an instability error here because you've released torsion, and that means that some element is free to rotate without load. So I would rarely release torsion, which is this last item here. Simply release, if you need a truss element, release rotation about the z-axis. Second most common error is your rigid body instability. So you'll get rigid body rotation about X. It means that this system is rotating or moving in the z-axis. So if you start getting that kind of error, I'd just be adding out of plane Z constraint to all of those nodes so that it doesn't move in and out of plane. The good thing is SpaceGas with later versions, it's removed this instability, so it's quite hard to get an out of plane instability error now. You've really got to remove your boundary conditions. But this is still, a very common error. Don't fully release the end moments because you won't be able to, you'll have a torsional instability. If you're creating truss elements, just release these two or these two, depending on the axis you're bending about. Okay, so let me just run through my checklist here. Units, geometry, properties, including your supports and instabilities, member fixities, section and material sizes. Great. Making good time. We've basically just got to the point that the generator has done for us. To practice all of that, what I'd recommend is using the structure generator and analyzing some system, get your results, and then try to create the structure manually. So there's no reason that you can't create all the geometry that the generator's built for you. Make sure that you can do that as a way to practice everything I just talked about. To actually analyze this though, we need some loads. So there's various types of loads, but really the only two you want to care about are node loads and member loads. If you select a bunch of nodes, select a bunch of nodes, and then this button here allows you to input node loads, or this loading button here also allows you to put node loads. Yeah. Again, it's very easy to kind of remember the order you need to do things because SpaceGas organizes it all in order. So you build your structure, build your nodes, build your members, build your node restraints, build your section properties, your material properties. That's all your attributes entered, and then start applying your loads. So your node loads, X, Y, and Z systems. I'll talk about load cases a bit later. Loads are in, linear static analysis. And then that's sufficient to start giving you some results. Deflected shape, bending moment diagram, axial loading, shear forces and reaction forces. Reaction forces there. I'm going to come back to results because I sort of skipped ahead there. I'm just going to go back to loading types. So if you click on the nodes, you can apply member loads. If you click on your elements, you can apply member, concentrated and distributed loads. So still going to put this in case 1. 2. Again, they're kind of parametric, so if you want to start and stop them at particular locations, start and stop them at particular magnitudes, you can control all that, but by default, they go from 0 to 100% of the element length, and your end values will be the same. The couple of things to pay attention to. By default, you'll be working in the global system, but if you need to apply a load that's inclined to your element, so say that you've got a portal frame that is 10, 3, 1. The portal frame wizard. If I want to apply a member distributed load as a wind load for this portal frame element, okay, the global system points straight down, but a wind load needs to be perpendicular to the element. So I want that load to actually be in the element's local system, which allows me to actually have it as perpendicular to the roof. If you've got a load patterning, again, as a wind load, you often need to apply a dropping magnitude of wind force. You can input a series of loads for the same case, for the same member. Oh, case 1, member 2, but you can change the subload. So you can do a change in magnitude of UDL across your member, like that. Oops, loads, member. Making sure that that's also in the local system. So that's, for example, a simple wind load pattern. Local system makes it perpendicular to the element, and then you can control the start and stop locations using the subloads to apply multiple loads to the same member. If you then also had self-weight, you can input that as a member distributed load as well. The problem there is if you change your section size, you have to change your load inputs. So to put in things like self-weights, it's probably better to use the actual self-weight load module, which automatically calculates a downwards member UDL in the global system, or at least, sorry, pointing in the direction of gravity, so -1g. So what I've just done, when I input this first load, I used case 1, and then when I input my self-weight loads, I called it case 2. Your load cases, you can name to make them more intuitive. So you could do uplift, wind uplift, wind downlift, downwards wind load, dead load, various types of short-term and long-term live loads. You can input them all as their values. And then you can use this load case manager tool to cycle between them. So dead doesn't show up as anything exciting. Maybe I'll put in a live load here to give us a third case. 5. Okay, so live load, wind load, and dead load. They're saved separately, and when we do our analysis, they're analyzed separately. So I redo my linear static analysis. Bending moment diagram from my wind load, from my dead load, and from my live load. A useful thing about specifying those loads separately is because you can then build combination load cases. So particularly for those of you who are going into Civil 3350 or are currently taking civil design, all of your actual design work will use a combination load case. It's not going to use an individual load like you might be seeing in some of your second and third year mechanics courses. What you can do really simply is once you've named or identified these individual load cases, oops, I messed that up, 0.2G plus 1.5Q, you can factor here. So these numerical factors are actually how much it's timesing your applied loads and then results by, and then it combines them together. But the title is just a natural language way of you explaining what these combinations actually are. Once you've got your combination load cases, SpaceGas will automatically superimpose results for that combined load case. So this will be 1.2G plus 1.5 Q, or 1.2 of your dead load plus 1.5 of your live load, the combined results there. You saw though, I accidentally overwrote the title for my first load case. So when you're numbering combination cases, give them a new individual load case number. So they're treated themselves like additional load cases. So if you have 3 normal loads, your combination load case should start at number 4. Loads, data sheet, local global self-weight, load case combinations. All right, so we're making pretty good time here, and we're going to keep moving at a quick pace. But please just jump in if you have any questions about anything. And now we're probably at the stage where you're kind of getting a bit beyond what's covered in your course. So some of this might be new information. In particular, I know in my third year course, I don't really tell you anything about load cases or load case combinations. Now, in analysis, linear static is always where you're going to start, but for many structures, probably most structures, we typically will also do something like a simple nonlinear analysis with p delta or second order effects as well. What that does, let's turn on labeling here, it will slightly change your results because it deforms the structure and then calculates the loads again. In many cases, that's not going to make much of a difference. So my analysis for linear static, my combination load case was, 8.39 kilonewton meters. If I analyze my nonlinear static case, which has second order effects, that's gone up to 8.45 kilonewton meters. So in many cases, your nonlinear analysis or your second order effects don't make a difference. Where they will make a difference is for things where you've got slender elements or you've got a heavy load at a large height, because it's basically a lateral deflection will cause eccentricity in your column. For most of your course questions, I don't necessarily think you'll be asked to do much second order analysis. You're probably told about buckling and p delta effects here and there. That's the computational analysis version of it. But in practice, often you'll be looking to run a second order or p delta effect analysis just to check that the side sway in your system is insignificant, or the deflection isn't significant enough to really change the structural geometry and then the load carrying capability. I'm mostly going to keep talking about linear static analysis, but I just wanted to point out that that is there. And there's also sort of things like buckling analyses and so on, which I won't go into. I'm going to drill a bit more into your results display. So over here, you can show your typical member forces. And you might have seen very briefly, I showed labeling and annotation. So once my forces are turned on, I can show on my diagram the actual numerical values. Often as you're jumping between load cases, particularly things like dead load and maybe a higher live load, the scaling seems pretty messed up. So this ruler allows you to scale to fit any of your diagrams. So if you're finding you can't read the information on your display, use this ruler to scale up and down your diagram, or scale to fit. Scale to fit. Then manage load cases. Okay, so deflection, bending moment, shear force diagram, axial loads, and then reaction forces. That's pretty standard. That's corresponding to a lot of how you're working through these problems in your courses. Something that's quite useful as a design tool, in the same way that load case combinations are useful as a design tool, is envelope. So you have a structure that's loaded under a whole bunch of load cases. You've got a wind load, a dead load, a live load, and then load case combinations. You might have 5, 10, 20 of these. And you need to design this element, and you have to design it for all load cases simultaneously and all positions simultaneously. You can show the results of the structure under typically all combination cases, but I've only got one, so let's say all load cases. Here are all of the bending moment diagrams for all of your load cases. What do you design for? Well, you can kind of try to pick out the minimum, maximum. Sometimes that's pretty obvious. Like here, that's your maximum hogging, maximum sagging. That's okay. This envelope tool also helps you to see that, because it will pull out the envelope case, which is the maximum minimum and the maximum. It's a weird way of saying it, but I think you get what I mean. The overall lowest and the overall highest value in that element for all of the load cases under consideration. Let me go to maybe all primary cases, bending moments. So you can see here now it's got this peculiar envelope shape, and that's because it's showing me my bending moment from my dead load, my bending moment from my wind load, and my bending moment from that live load all together, and it's pulling out the overall minimum and the overall maximum across that entire element for all those selected load cases. So the envelope tool is quite useful as a design tool, and it relates directly to your load cases. So as soon as you start inputting serious load cases, I'd also start recommending that you play with your envelope tool here, just to give you a little bit more insight into what loading is actually governing or potentially governing a member behavior. The last thing that I'll say on results, and in fact this will probably wrap up everything I wanted to talk about today, just about, is the output. Well, there's two things. SpaceGas has very sophisticated design tools. You can basically automatically design your steel sections, your steel connections, and your concrete sections. I would not recommend you do that as a junior engineer, or you only use it to check your own design calculations. And I don't know of too many firms which use this design tool, except for very routine designs, which they're quite confident in sizing up anyway, or they're able to check the SpaceGas results pretty easily. But having said that, design is parametric. It's just a parametric tool that sizes something to AS4100 or whatever your concrete design code is, 3600. But the last really main thing I did want to talk about was the output. So the graphical interface is fine, but to actually export your data, you can generate text reports, which then you can process much more robustly. So if you're interested in your member forces, you can just select what you want. You can select the how they're sorted by load case or by elements. Elements typically more useful, and then you can see a summary for your loads in all component directions. And now this is the kind of thing you can copy paste into Excel, or you can open with Python as a CSV file or something like that, and you can actually batch process, what is the governing loads, or what are the minimum maximum moments that I have to look at. Again, though, that's getting pretty advanced, and I wouldn't expect you to need that as an undergraduate, but it's a useful capacity for the future when you start getting into larger analyses. Okay, there's one final thing to show you. It's nothing super exciting, unfortunately, but it is kind of useful. The SpaceGas website, spacegas.com, has pretty decent quick start guides and training videos. So even for me giving this presentation, there are a couple of things I wasn't sure about, particularly in concrete. which I haven't used very much. It actually has really great videos on every topic. So if you want to develop a basic capacity for literally any of those tools that I just showed you, plus a whole bunch more besides, these are just 3 to 5 minute videos, which will pretty much get you up and running straight away. And they cover, you know, all of the basics, plus a whole bunch otherwise. It even has some stuff towards my end of the neck of the woods where you're trying to connect this to things like Grasshopper, or connected to things like Revit Structure, or importing things from some of the CAD packages which might have your geometry in it. And yeah, like all analysis software, it's constantly adding tools, computational tools, whether that's for internal parametric design or interoperability with other softwares. But once people get to using this end, most of the people I know who operate at this level of interoperability tend to develop their own parametric tools rather than just learn how to use the inbuilt ones in the software. Okie dokie. I think I covered a lot of stuff there. At least I felt like I was talking very quickly, but are there any questions? Hopefully that was reasonably clear and gave you a pretty good primer on all the key things to pay attention to.
And none from me. That was great. Thank you.
Okay, well, thank you very much. Happy, of course, always to answer questions on email or anywhere else you can track me down. If there's questions people have in the chat, I might just answer them directly rather than on audio. So thank you.
Awesome. Thanks very much, Jerry.